Integration by parts is an analog for integration of the product rule for differentiation. It's usually used to integrate products of functions that we have no other way of integrating. Let's start off with the formula for the product rule. Remember that the derivative of the product uv is uv prime plus u prime v. Let's do a little algebra to that, and we'll take this term over to the left and then swap it around. So we get uv prime is derivative of uv minus u prime v. Now let's take the integral of both sides. So the integral of uv prime dx is the integral of the right-hand side, which is then the integral of this term minus the integral of that term. But this is the antiderivative of the derivative of uv, so this term is just uv. So that gives us this formula, which is the integration by parts formula. So it doesn't look too helpful because it's replaced the integral of one product by the integral of another product. The key in using this is to set it up so that this product on the right-hand side is easier to evaluate than the one we started with. So let's have a look at a quick example. Let's do x cosine x. So we'll take u to be x and v prime to be cosine x. So a question we get a lot is, why did we do it that way around? And the answer is usually because this gives us a simpler integral over here. We can integrate cosine and get sine and differentiate x and get 1, and then the integral we get on the right-hand side is going to be simpler than the one that we started with. So as I said, u prime is 1, v is sine x. So what happens when we apply the formula? We get uv, that's x sine x, minus u prime v, that's 1 times sine x. So this is just x sine x minus the integral of sine x, which is the integral of sine x is minus cosine x, so the two negative signs cancel out and give us a final answer of x sine x plus cosine x plus c. So you see it's fairly straightforward to implement once you get the hang of it. A couple of examples to try are x sine x and x e to the x. They're similarly straightforward. With integration, of course, you can always check your answer, and it's a good thing with integration by parts to do this now and then, just to see what's happening and to check that you've got the right answer. So here, let's try to differentiate the right-hand side. The derivative of x sine x plus cosine x is, well, we apply the product rule for this thing, x cosine x plus sine x, and then we differentiate cosine x and get negative sine x. So these two signs cancel out and it gives us x cosine x. So we have indeed found the right antiderivative of x cosine x. So that's the basic principle. Now let's look at a few twists and subtleties that we can add to this basic formula. The first one is definite integrals, which we often want to do. So the definite integral version of this formula has limits from a to b on both of the integrals, and for the uv term, it's the straightforward evaluation of this function at b minus its value at a. So let's look at an example of applying that. Let's do the integral from 1 to 2 of x log x. This time, because we don't know the antiderivative of log x, we can't set it up in the same way we did last time, with u being x and v prime being log x. So we have to reverse roles. This looks like it's going to make things more complicated, but in fact it turns out to work. So we take u to be log x, v prime to be x. So u prime, as we know, is 1 over x, and v, the antiderivative of x, is x squared over 2. So we plug everything into this formula and we get the following. So it's a bit of a mess, so let's talk through it slowly. So this is what we're looking for. This is u times v, evaluated between 1 and 2, x squared over 2 log x. And then here we have u prime v, 1 over x times x squared over 2. So we just continue with this. Evaluating this, we should get 4 over 2 log 2, that's 2 log 2. And then when we evaluate at 1, we should get a half log 1, so this 1 should actually be a half. But the log 1, of course, is 0, so I won't worry about that. And here we have plus the integral from 1 to 2, x over 2 dx. The antiderivative of x over 2 is x squared over 4. So we just need to evaluate that between 1 and 2, and that gives us 4 over 4 minus 1 over 4, which eventually gives us a final answer of 2 log 2 minus 3 over 4. Another little trick, surprisingly, is that one can use the integration by parts formula when there's no obvious product. This is somewhat surprising, and it only really works for 2 or 3 situations. One is the antiderivative of log x by itself. Another one's arctan x. So let's look at the arctan x example. So the only way we can write this as a product is to take v prime to be equal to 1 and take u to be arctan x. So u prime is then 1 over 1 plus x squared, and v is x. So let's put it all in and see what happens. The first term, the integral we're looking for, the integral of arctan x, is equal to uv, x arctan x, minus x over 1 plus x squared. Now, this is why integration by parts works surprisingly in this situation, because this integral we can integrate using substitution. We take the substitution u equals 1 plus x squared, du is 2x dx, so we end up with a half 1 over u du, which becomes a half log 1 plus x squared. So I didn't write that down. If you have any issues with it, just take out a pencil and paper and do the substitution, and you'll see that it comes out easily. So here we get the somewhat surprising answer that the antiderivative of arctan is x arctan x minus a half log 1 plus x squared. So just as an aside, this is another interesting situation which shows that these functions that we initially kind of constructed in very different ways turn out to be closely connected. The arctan function you wouldn't really expect to have very much overlap in any way with the log function, but here it is coming out in a very close connection in the way that the antiderivative of arctan involves log 1 plus x squared. So an interesting thought, but let's stop with the philosophy and move back on with techniques. The next technique we want to discuss is repeated application. So often this integral on the right won't actually be immediately, we won't be able to immediately calculate it, but it will be simpler and we'll be able to apply integration by parts a second time or a third time and eventually get the answer. So let's look at a classic example of this. It's x squared e to the 2x. So we take u to be x squared, v prime to be e to the 2x. U prime is 2x, v is, remember, 1/2 e to the 2x. When we take the antiderivative, we divide by this factor. We plug all this into the formula. uv is x squared times 1/2 e to the 2x. U prime v is all this stuff here, 2x times 1/2 e to the 2x. So we get 1/2 x squared e to the 2x minus the integral of x e to the 2x dx. So here's exactly what I've been describing. Integration by parts produces another integral that we have to use integration by parts on, but this one's easier and is going to terminate, as it were, with one application of integration by parts. So let's just hold this thought here, hold this formula, and let's go and calculate this integral separately as a little digression, and then we'll come back and substitute it into this formula. So just to kind of emphasize the digression, I'm going to do this in blue. So we're going to calculate this in the same way. We take u as x, v prime is e to the 2x, u prime is 1, v is a half e to the 2x. Plug it all into the formula. We get uv, x 1 half e to the 2x minus the integral of u prime v, which is just the integral of a half e to the 2x. So this term's just 1 half x e to the 2x. This one, when we integrate this, we divide again by 2. So now we have 1/4 e to the 2x plus c. So that's that. Now we go back and substitute that in here, remember? So the integral we're after is equal to 1 half x squared e to the 2x minus this thing here. And so that gives us minus a half x e to the 2x, and remembering to distribute the minus sign, plus 1/4 e to the 2x. And we don't have to worry about the minus sign with a c, because this is really just a symbolic thing saying plus a constant. So it doesn't really matter whether the constant's plus or negative. So that's a brief introduction to integration by parts. There are some more twists and turns that I'll talk about in another video, but this is enough to get started with. The only way to really get good at integration by parts is to do a lot of examples and become familiar with the kind of situations where you need to use it. There aren't, in fact, that many different problems that you're likely to be asked in integration by parts. So the more problems you do, the more comfortable you'll be with anything you can be asked.